Okay, so what we're going to talk about today is solubility, kind of in relation to acid and base chemistry and equilibrium. And so we're going to start out talking about KSP. And what KSP is the solubility product constant. It is an equilibrium constant. And what it is the equilibrium constant for is for an ionic solid and its saturated solution. So one of the things to keep in mind for KSP is that the reaction is always considered from the point of a dissolving solid. So the solid compound is always the reactant, and the ions in solution are always the products, which would mean it has a basic equation like this, where this is a solid, these are both aqueous, right? And this would have some balancing numbers perhaps, and the equilibrium expression will always look like this, where you have a to the n and b to the m, right, if those were balancing numbers here. All right, and that's going to be your equilibrium constant. Make that a little more like an m. That's really a disaster. Okay, so, right, that is the basics of KSP. It is just an equilibrium expression. And to go along with that, we have the common ion effect, which I know we've talked about a little bit before, but here we'll talk about it again. We can say that the solubility of a slightly soluble salt is decreased by the presence of additional solutes that contribute common ions to the solution. So basically, if you're trying to dissolve something and you put another substance in there that contributes one of the ions as the same as something that you're trying to dissolve, whatever you're trying to dissolve will end up dissolving less. As an example, right, we're going to say what is the molar solubility of calcium fluoride in a solution that also has sodium fluoride at a concentration of 0.01 molar, with the KSP of calcium fluoride being 3.9 times 10 to the negative 11. So we start by looking at our dissolution equation here, where we have calcium fluoride in equilibrium with calcium and fluoride ions. And then we draw ourselves an ice table, because everybody loves ice tables. And so we start out with 0 of our calcium, right, because sodium fluoride is not adding any calcium to our solution here. But we have 0.01 molar as our concentration of fluoride already, right? Because that's the concentration of our sodium fluoride, and sodium fluoride is going to completely dissolve. So we know that the concentration of this is equal to the concentration of this initially, right? And then for our change, we are adding calcium, and we are adding 2 fluorines for every 1 calcium, right? Because that's our balancing number here. So then the change, right, is x at equilibrium, and 0.01 plus 2x for fluorine at equilibrium. And now we can look and say, can we get rid of those x's? Of course we can, because our KSP is definitely less than 5% of our concentration. So we end up with this, where we have our KSP equal to our concentration equal, or x times our concentration of fluorine initially squared, right? Because the squared comes from here. And if we do that math, we can switch it around to look like this, and we get a concentration of calcium is 3.9 times 10 to the negative 7th molar, which is not a lot. It's a pretty small concentration. So as a aside, I forgot what this number was for a second. As an aside, right, under conditions where there is not already fluorine, right, the molar solubility, or the amount that would dissolve here, the concentration of calcium fluoride would be 2.1 times 10 to the negative 4 molar. All right, so it's a pretty big difference just by adding some sodium fluoride. Okay, pH and solubility. So the solubility of an ionic compound containing a basic anion, so that's the conjugate base of weak acid, increases as the pH decreases, right? So things that contain basic anions, right, ionic substances that contain basic anions, increase as the pH decreases. So as something becomes more acidic, it can dissolve more of an ionic compound containing a basic ion, right? So, for example, magnesium hydroxide, all right, it has a basic anion in hydroxide that is definitely basic. It dissociates into magnesium and hydroxide. Now, the other reaction that we are concerned with is that when you react hydroxide and hydrogen, you make water. And so this becomes a simple Le Chatelier's principle situation where if you are trying to dissolve as much magnesium hydroxide as possible, right, and knowing that it produces both magnesium and hydroxide, if you are adding acid to this system right here, right, you're basically removing reactants. Right? And anytime you shift the balance of an equilibrium, you're going to move things in that direction, right? So if you're removing products, you're going to shift the equilibrium in the direction of products, right? So you can dissolve more magnesium hydroxide in an acidic solution. So this also plays into formations of complex ions, right? So the solubility of metal salts increases with the presence of a Lewis base with which the metal will form a complex ion, right? And so as I say here, you saw this in the Le Chatelier's principle lab that we did. And so if we take this reaction where we're dissolving silver nitrate, which was one of the things that was dissolved in the lab, and you add ammonia to it, right? You are producing ammonia or silver, a silver ammonia complex, right? This thing right here. Now, the same thing is going on here as with the acidic solution, right? You're producing silver and you're producing nitrate. And then here you have a reaction where you're combining the silver and forming this silver ammonia complex, right, which basically means you're removing silver from your equilibrium here, right? You're taking it out of this equilibrium expression, which pushes the equilibrium to the product side, meaning that that silver nitrate is going to become more soluble in a solution where you have you have a Lewis base, right? This thing present that will form a complex with the ion in question. All right, so this is really just a situation where you have a Le Chatelier's principle thing going on. You're removing your metal ion, and that's pushing your equilibrium to the product side. Okay, now here we really get into the equilibrium calculations when we want to selectively precipitate ions. All right, so when you have a solution with multiple species of ion present, the KSP and identity of the individual ions can be used to precipitate each ion individually. Thus, you can separate the components of a liquid mixture where they are all dissolved, right? And so this often involves looking at precipitation in terms of Q versus KSP. And if you remember from the equilibrium unit, Q is the value that, or the current conditions that system lies in, and you look at that in relation to the equilibrium constant to decide which way something's going to go. So, right, when Q equals KSP, that is at equilibrium, or in this case, the solution is saturated, and any additional solute will cause a precipitation, right, because you're going to throw it out of balance from equilibrium. So when Q is less than KSP, right, that means you have not met your equilibrium situation yet, right? You're not there yet. So more solute can be dissolved without precipitating out a solid. And when Q is greater than KSP, right, you have gone beyond your equilibrium value there. A precipitate will form under these conditions because you're beyond saturated, and so a precipitate will result. So, of course, there are some examples that will go along with this. So the two examples that we have, well, the first one, does a precipitate form when 0.1 liters of 8 times 10 to the negative third molar lead nitrate added to 0.4 liters of 5 times 10 to the negative third molar sodium sulfate, right? So will a precipitate form when those two are added together? And we'll think about the KSP for lead sulfate being 6.3 times 10 to the negative 7, right? We're not concerned about the KSP for sodium nitrate because, as you know from the solubility rules that you have memorized, column 1 metals and nitrates are pretty much always soluble. So we're only concerned with lead and sulfate. So this is the dissolution reaction. I should have put an equilibrium arrow in here, so let me fix that. There you go. Right, so we're forming lead ions and sulfate ions, right, and this is our ionic substance. And so basically, we are going to figure out the concentration of each of these substances in our final solution to see if something is going to precipitate. So first, we're going to look at lead. We start with 0.1 liters at this molarity, right? 8 times 10 to the negative 3 moles per 1 liter. Our final volume of our solution, right? 0.1 plus 0.4, right, is going to be 0.5. That's the final volume of our solution to give us our final concentration of lead. Now we're also going to do that with sulfate, right? Same deal. We started with 0.4 liters of it, this many moles in 1 liter, divided by the total volume of our solution, and we have 4 times 10 to the negative third molar as our concentration of sulfate. And so then what we're going to do, we're going to write our equilibrium expression. So if you remember, right, KSP is equal to PB and SO4, right? Or we can say Q in this case because we're not sure if it's at equilibrium. And so Q, right, is going to equal the concentration of those two things multiplied together, right? No exponents because neither of them has a balancing number. So we get that as Q, right? And so then we can compare that to KSP, right? So if we compare that to 6.3 times 10 to the negative 7, we know that Q, right, is greater than our KSP. So, right, in that case, if you think back to the last slide, when Q is greater than KSP, a precipitate will form because our current conditions are beyond the solubility of that particular compound. And so when we mix these two things together, we will get solid lead sulfate out of that reaction. Okay, the next example. We have a solution that contains 1 times 10 to the negative second molar silver, ions and 2 times 10 to the negative second molar lead ions. What concentration of chlorine or chloride is needed to begin the precipitation of each salt? Which salt will precipitate first? So we look here, we know the KSP for silver chloride, and we know the KSP for lead chloride. And I think looking just at those KSPs, you could probably tell me that silver chloride is going to precipitate first because it has a much smaller KSP, but we're going to do some calculations and find out if you are correct. So keeping in mind that for our lead chloride, right, or sorry, silver chloride, we'd be looking at AgCl in equilibrium with Ag and Cl minus. All right, so we have KSP is equal to Ag times Cl, and we know the value of that KSP. And so if we're looking for concentration of chloride in this case that is needed to make this precipitate, right, we rearrange this to solve for chloride, right, where we have KSP over Ag equals Cl, which means we have the KSP over the concentration of silver. And when we do that math, we get 1.8 times 10 to the negative 8 molar. So this is the concentration of chloride at which silver chloride will start to precipitate out of this reaction. So then we look at our lead situation. Again, our KSP is equal to our 2 ions, but in this case, right, if you notice, PbCl2, which means we're going to get 2 chloride ions for every 1 lead, which we're going to have to take into consideration when we go to calculate the concentration of chlorine. So when we rearrange this, right, we're going to need the square root of KSP over Pb2 to get rid of that exponent 2. So when we have these numbers, right, our KSP value and the concentration of lead, and when we do that math, we get 2.9 times 10 to the negative 2 molar, right? So much, much higher concentration is needed to precipitate out lead. So what we can tell from these two numbers here, right? Silver can be separated from lead by precipitation, right? What we need to do that is we need to keep the chloride concentration between 1.8 times 10 to the negative 8 and 2.9 times 10 to the negative 2, right? Because as long as the concentration is above this, silver will precipitate, and as long as the concentration is below this, then lead will not precipitate. All right, so that's what we need to do, and that means that we can separate these two metals in this particular solution. All right, so that's all we've got for that. That is the end of that unit, and we will soon be moving on to thermodynamics. I'll see you in class.